We have seen in the previous lectures counting sort that can sort in linear time if the numbers are small. In this lecture, we're going to see radix sort, which is an extension of counting sort that can also handle larger numbers and still achieve very good time. Really, all the power of counting sort comes up when you do the radix sort extension. In radix sort, the assumption is that all the elements of the input array are integers with d digits. Okay, we're going to think of the numbers in a certain base. And the key idea of radix sort is to first sort the integers by the least significant digit, then according to the next digits, and so on and so forth, until finally you sort according to the most significant digit. It is essential for radix sort that the base algorithm that you use to sort with respect to each digit is stable. Stable is a keyword in the theory of sorting, which means that elements with the same value for the digit will appear in the output array in the same order as in the input array. Okay? To think of stability, you really have to think that your elements carry some additional information in addition to the key with respect to which you're sorting. Okay, in the case of radix sort and numbers, you sort only with respect to one digit, but the other digits also carry information and you want to preserve the information in a certain way, and that's stability. And there is a fact which we're going to utilize that counting sort is stable. Okay, and you can verify that by inspecting the pseudocode. Okay, so again, radix sort for an array A from 1 to n proceed as follows. You start with an index I that goes from the least significant digit to the most significant digit. And for each value of I, you use a stable sorting algorithm like counting sort to sort the array A with respect to that digit. Here is an example. Let's sort in increasing ascending order 3210. Okay, and we're going to think of them as two binary digits. So my input is the array where the first entry is 1 1, that's binary for 3, then 1 0, that's binary for 2, then 0 1, that's binary for 1, and then 0 0. Okay, so what we do at the beginning is to sort with respect to the least significant digit, which is this one. This corresponds to whether the number is odd or even. Okay, so when we sort this, well, first we should put the things which have 0 in that location. Okay, so first we put this 0 here, so it's 1 0. Then the next thing would be 0 0. Then you will have the ones with have a 1 in the digit, that's 1 1, and then 0 1. The fact that the sorting algorithm is stable, it means that, for example, these two entries, which have 0 in the digit, have not crossed. They have maintained the relative order when we sort with respect to the digit. Next, we sort with respect to the more significant digit. Okay? So first we put the ones which have 0 there, so that's 0 0, then 0 1. Then it comes the ones which have 1 there, so that's 1 0, and then 1 1. Okay? That's exactly what I wanted, because 0 0 of course is equal to 0 in standard base 10. Then 0, 1 is 1, 1, 0 is 2, and 1, 1 is 3. So I've sorted correctly my array. Here is another example with 3 digits that I've taken online. So here I have 12 entries, and each entry has 3 digits, and the digits, for simplicity, here are letters. Okay. So at the beginning, we're going to sort with respect to the least significant letter. Okay, so that would be so it's accomplished here. That means that you have first all the B's, then all the D's, then finally the E. And then we sort with respect to the middle digit. So then you have first the A's, then B, C, D, and then all the E's. And then you sort with respect to the most significant digit. Okay, and again, stability means that when you sort with respect to the same keys, the relative order is preserved. For example, here you have this entry has a D here, a D here, D here, D here, D here, D here. You can see where they go, and you can see that the relative order is preserved. The sorting will not be stable if these arrows crossed. Let's analyze the running time of Radix sort. Let's call the T of n the number of operations of Radix sort. Well, it's clear that T of n is D, the number of digits, times the running time for counting sort in n elements. As we saw earlier, the running time for counting sort was n plus k, where k was the maximum value for integers from 0 to k. So that's theta of d times n plus k. And here is a cool example. Let's say you want to sort numbers in the range 0 to n to the power 10. How much time will it require? Well, I want to pick a good basis, okay? And the idea is that I want to think of my numbers in base 10, in base n, okay, in base n. If you think of the numbers in base n, then you have only a constant number of digits. Okay, so the running time will be theta of n. D would be a constant. While if you were to apply just plain counting sort to such an input, it will take much longer. It will take time n to the 10. Okay, so here we can see that we can sort in linear time even integers of polynomial magnitude, like n to the 10, n to the 100. This is very powerful because such integers arise in many applications. Let's finally also consider the space of Radix sort. And well, we need as much space as we need for counting sort on each digit, and that was n plus k. So naively, we do this d times, so the space is order of d times n plus k. But this is a very loose count. You can improve on this. And the idea to improve this is that you can reuse the space across digits. Okay, so once I've sorted with respect to one digit, I have a new input and I can forget anything else. Okay, so the space in this case will be just order of n plus k. Okay, you don't have a dependence on d. You sort with respect to one digit, you have your output, then you forget anything else. Then you sort with respect to another digit, and so on. The only thing that you need to remember is which digit you're at, and that takes constant space. So we are seeing some very fancy ways in which you can sort in linear time, but we need additional assumptions like the numbers are small. So a natural question is whether you can sort faster than what you can get with bubble sort, which gives n squared without extra assumptions. And in fact, later in this class, we're going to show how to sort with just order of n log n comparisons. Okay, so not linear, but close to linear if your comparisons are fast. This is pretty close to linear. And we use that as an excuse to introduce a new general paradigm, divide and conquer, which we're going to see in the next lectures. That's it for now.